So, today we will discuss about density of seawater. Now, density is important from the point of view of ocean circulation. So, primarily if we want to have a look at density, so density determines depth to which the water will settle, or depth to which water particle will settle in equilibrium. So, this is the defining parameter for density. So, here you will find the least dense water present on top. So, this is quite natural, present on top and densest at the bottom. At ocean bottom. Now, mixing is easiest. Mixing of seawater is easiest in waters having same density. So, this point is to be noted, because maps of density surfaces So, these are called isopycnals. Pycnals. So, these are surfaces having the same density. Iso means same, pycno is another term for density. Density are the same. So, these are mapped, and these maps are used to depict circulation patterns. So, density is a governing parameter for ocean circulation. So, depiction of circulation patterns. Now, how density is given? So, density it is given in terms of this parameter called rho, and rho is equals to 1000 kg per meter cube at 0 degree centigrade. And no salt. Now, seawater density is 1021.00 kg per meter cube. This is at sea surface. Now, normally the sea surface is designated with P equal to 0, that pressure equal to 0, or atmospheric pressure. So, 1021 kg at sea surface, and this becomes 1070 kg per meter cube. This is at a pressure of 10,000 decibars. So, this is almost at 10 kilometers from the ocean surface. So, density, there is a variation in density. Now, common method of describing density is by this parameter called sigma. So, sigma, S stands for salinity, T is temperature and P is pressure. So, this is given in terms of density above 1000 kg per meter cube. So, in oceanographic literature you find this parameter called sigma STP. So, this is called in situ density. In situ density calculated at sea surface. So, this is how the density is defined, and there is another equation which is to be noted, that is density is also given as an equation of state. Equation of state for seawater. So, this is given, instead of writing in situ density, you simply write rho in terms of salinity, temperature, pressure, and this will be rho in terms of salinity, temperature and pressure, you take it 0. That means, at the sea surface divided by this factor 1 minus P divided by K. K is called the bulk modulus. So, this is another expression for density. So, salinity, temperature and pressure, at any pressure on the below the sea surface, it is linked with rho ST0 at sea surface 1 minus the pressure at that point K STP stands for your bulk modulus. Now, this equation also can be written in this form. Now, K here stands for bulk modulus. Now, here actually this is a slightly different formula, but this also nowadays is used. So, this stands for density at any point. So, this is your rho 0 plus, you can represent this in more mathematical form. So, T minus T 0, I will give you what this T 0 rho 0 stands for, and alpha beta are constants, S minus S 0. So, this is your equation. Now, alpha is the density gradient. So, this is delta rho divided by delta T. So, change of density with respect to, amount of change of density with respect to T stands for temperature, and beta stands for what? This will stands for change of, remember your parameter is your density. So, this will again be delta P, delta rho divided by delta S, that is change of density with respect to salinity. So, alpha stands for change of density with respect to temperature, beta stands for change of density with respect to salinity. and this rho 0, T 0 and S 0. So, this represents the density, temperature and salinity. You can take these are at any point are arbitrary constants, but normally you can take them at the sea surface. Now, please do not talk. And rho T S, these are mean values for the region. Now, if you take the spatial region in the ocean, obviously it will vary according to your x and y values. So, you just take the mean values. So, this gives the rho, that is the density at that particular location with reference to some rho 0, T 0 and S 0 value. Normally, you can take this at the sea surface if you like, or at any other point. So, this gives us the equation for state linking density, temperature and salinity. So, this equation of state actually models these three terms or links. So, this is vital for defining your density, links density with temperature and salinity. So, that is why this equation is more preferable to the one that having that bulk modulus k. So, this is the equation of state, and with this we finish our discussion on density. Now, there is a problem on this current. So, last time we discussed about geostrophic current. So, this is an example of a geostrophic current. Now, in the northern hemisphere, you will come across this huge current which is called the Gulf Stream Meander. This is called Gulf Stream. So, this is quite famous current. This is called Gulf Stream Meander. Now, this current actually goes from the eastern coast of to the coast of United Kingdom. So, UK is somewhere here. So, this is called the Gulf Stream Meander. It flows from the northern hemisphere like this and it goes towards the UK coast. So, this is one of the main reasons for why you get on the eastern shores of UK you get the warm current, but whereas on the west coast you get a very cold climate. So, this is the reason of called the Gulf Stream Meander. So, this occurs in the northern hemisphere. This occurs in the northern hemisphere. Now, let us try to calculate the velocity of this current. Now, in the problem this is given as pressure change across you have to calculate this pressure change. So, pressure change across Gulf Stream. Is the result of an increase in sea level. And this value is 1 meter. Now, this takes place over a distance across Gulf Stream, across Gulf Stream of 100 kilometers. So, pressure change results in a sea surface elevation of 1 meter. So, in brackets you can write this as delta Z over a distance across 100 kilometers. So, this is your delta x. Now, you calculate the geostrophic current. So, you first you get the hydrostatic balance equation, or simply write down the hydrostatic equation. So, what is the hydrostatic equation? So, this is given by delta P is equals to rho g delta Z. So, this is your hydrostatic, also sometimes this is called a hydrostatic balance. So, this is actually supporting the weight, that is why this is called hydrostatic balance. Now, in the northern hemisphere, what is happening, your flow, let us see, have a look at the direction of the flow. So, this is your low pressure region. So, this is a pressure of low pressure. So, these are your pressure or lines of equipressure. And right at the bottom you have high pressure. So, in which direction the flow will be directed? So, flow is always directed from high pressure. So, this is a region of high pressure. So, flow is always directed from high pressure to low pressure region. So, that is your driving force. Your flow is going to go like this. So, this is called the Gulf Stream meander. And why towards the right? So, your velocity vectors will keep on increasing. Now, till at a certain latitude you will find the flow is becoming horizontal. Now, at this region you will find your pressure, that is given by FPG. Your pressure force will balance the Coriolis force, FCF. So, in bracket I am writing this as pressure. Pressure force is going to balance your, this is FCF, is the Coriolis force. Then you get the velocity of the flow. This is given as Vg. So, pressure equation I have written. Now, you write down the equation for geostrophic current. This is called geostrophic current. Now, in the northern hemisphere, I have told you the flow is always directed towards the right. You suppose you are throwing a particle from the equator to the pole. So, that will have its own velocity, plus you add the vectorially add the rotation of the earth, which is in the from left to right. So, your particle will always get deflected towards the right. So, this is a result of the Coriolis force or Coriolis acceleration. Now, in this case the geostrophic current you have to calculate from V g, this is equals to 1 by rho f. Now, f is this is the Coriolis factor multiplied by the pressure gradient. So, del p over del x. So, this is your pressure gradient and this value is given, and f you take it as twice omega sin phi. Now, omega is your Earth's angular velocity. So, since this is a geostrophic current or Coriolis, it has to be linked with the velocity of the Earth or Earth's angular velocity. So, this is equals to 7.29 into 10 to the power minus 5 radians per second. So, this is the angular velocity of the Earth. Now, this phi is latitude. Anyway, so from this equation you can calculate the value of f. Now, for calculation of V g, this value of f is already given. Now, V g is equals to 1 by rho f into del p over del x. Now, you substitute how much is the value of del p. We have found out del p from the hydrostatic balance equation, and what is that value. So, this is equal to 1 by rho f, del p is nothing but rho g delta z. Now, you divide this by rho f, what else we have got? Delta x. So, ultimately you can see we are getting delta z over delta x. So, rho will cancel out, g divided by f. So, the final equation we will get as g over f multiplied by delta z over delta x. Now, value of g is in centimeters, this is 980 centimeters per second, and f is given as 10 to the power minus 4. So, this is radians per second. So, at that particular latitude, what is the angular velocity? Now, what is the value of delta p? Sorry, delta p we have given this is delta z. Now, delta z is given as 1 meter. So, 1 meter you are doing it in centimeters. So, obviously, this will be 100 centimeters, and this is the elevation over how much? Delta x value is 100 kilometers. So, you convert that into centimeters. So, this will be 10 to the power 7. Now, you reduce this will be approximately this will give you 100 centimeters per second. It is coming. So, approximately I am writing this. So, this is 100 centimeters per second. So, geostrophic current velocity V g is 100 centimeters per second approximately, although you are getting this as 98. So, this is the Gulf Stream velocity. centimeters per second. You see the units where it is right or wrong. So this is 100 square. So this is 5 minus 4 is how much? So you are getting almost, and this okay, 98. Yeah, centimeters per second. Almost 100 centimeters per second. So that is your Gauss stream velocity. So with this, let us finish about the properties of seawater. Now next, let me start about the linear wave. So how one gets this wave equation? So your wave equation, if you calculate the wave equation, this comes from the equation of continuity. So what is this equation of continuity? So this is given as del u, or rather you can write del u x over x plus del u y over y, del y plus del u z over del z equal to 0. So equation of continuity is what? What is the significance of equation of continuity? So I am not going into details. This you ask your hydrodynamics teacher how he has got the equation of continuity. Equation of continuity is coming from conservation of mass. So this is your equation of continuity. Now you substitute these values of ux, uy and uz. So ux is how much? It is del phi over del x. Uy is del phi over del y, and uz is del phi over del z. Now you substitute these values in the equation of continuity and see what you get. Now if you substitute this, you will get the Laplace equation. Are you getting it? So you substitute this, so this will be del square phi del x square plus del square phi over del y square plus del square phi over del z square. So this is equal to 0. Now this in mathematics they term this as nabla square phi equal to 0. So this is your famous Laplace equation. Now the linear wave, or sometimes this is called the airy wave, is nothing but a solution of this equation. So a linear wave or an airy wave is the solution of the Laplace equation. So you remember this. Solution of Laplace equation Now, what is this equation? Equation in short is written as lambda square phi equal to 0. Now, if you look at this solution, you will find this solution is written in this form as eta x t. Eta is varying with the position x and the time t. So, this is given as a sine of omega t minus k x. So, this is your elevation for linear wave. If you draw a graph, this will look like this. Now, later on we will at the end of the class, next class we will go and have a look at nonlinear waves. But before that, let us explore this. And what we have to be careful about is the application regimes of the linear and nonlinear waves. So, this is what? This is one wave period. Now, the horizontal axis can either be t or x. Since your surface elevation eta is called the surface elevation at any point of time. Now, what is your A? A is your amplitude. A is amplitude and T is called the wave period. And L is the wavelength. Now, since I have selected one horizontal axis, you can depict this as T and L. Then what is wave height? And H is your wave height. So, that is the distance between the trough and the crest. So, these parameters are the physical parameters of the airy wave. Now, you calculate the speed of propagation. Now, this is not a standing wave, it is a propagating wave. Now, a propagating wave has certain velocity, speed of propagating wave. Now, if you want to calculate this, then this angle, that is omega t minus kx, is referred to as phase angle. Now, there is a simple method of calculating the propagating wave velocity. You simply take the partial derivative of this phase angle to be 0. That is, the phase angle remains constant. This is equal to partial derivative of omega t minus kx is equal to 0. So, this implies that phase angle remains constant. Obviously, the partial derivative of remains constant. That is, the derivative of a constant will obviously give you 0. Now, what is, you differentiate this with respect to time, how much you get. So, this will be del omega t over del t minus del x. First you differentiate this with respect to x, then you multiply this by dx dt. So, this is equal to 0. Now, from this we get omega minus k dx dt. So, this is equal to 0. So, now you can find out the velocity. So, dx dt is how much? So, that is our linear velocity of the wave. So, this is we are getting this as omega by k. Now, omega is how much? Omega is called the omega is equals to 2 pi omega is the circular frequency and k is the wave number. So, omega is the circular frequency. And k is 2 pi over, in this case it is L. So, this is called wave number. So, remember the expressions for this omega and k. The omega is 2 pi by t, t is your wave period and k is the wave number is 2 pi by L and L is the wavelength. So, omega by k, how much it comes? So, this is 2 pi by t over 2 pi by L. So, this comes as a very neat relationship of L by t. And sometimes this is given as c, that is the propagating velocity. So, this is called speed of propagation. So, we have got the equation for the surface, that is the airy wave, that is given by eta, and we have got the c, that is the velocity of propagation. Now, you find out what is the particle velocity. Now, your surface elevation equation is eta x t. So, this is we are using a sine wave a psi, that is omega t minus k x. So, actually there are two variables, one variable is t and the other variable is x. Now, you have to define a velocity potential. Now, this velocity potential has to satisfy the Laplace equation for this surface profile. Now, this is your velocity potential. Cos hyperbolic k d plus z divided by sine hyperbolic k d and cos omega t minus k x. So, this is the velocity potential that is to be used. This should satisfy your Laplace equation. satisfy nabla square phi equal to 0, the Laplace equation. Now you find out particle velocity. Now we are considering the wave in 2 dimensions, that is x and z. So particle velocity, or rather you can write water particle velocity, ux, the horizontal water particle velocity. And the other one is uz. So this is your vertical water particle velocity. Now, so what is the expression for ux? Now, ux you get if you differentiate the velocity potential phi with respect to x, and uz you calculate from del phi over del z. Now, later on you will find if you want to calculate the pressure term, you will require ux and uz. Your ultimate goal is to find out the pressure term as an ocean engineer. Anyway, so that will come later on. Now you find out what is this value of ux. Ux is del phi over del x, and phi we have got the expression for phi. Phi is this expression. So you differentiate this with respect to x and see how much you get. So ux will be omega a into, there will be 2 minus sign coming from where minus k will minus will cancel out and k will also cancel out. So you will get this expression, cos hyperbolic of k d plus z and this is divided by sine hyperbolic of k d. And if you differentiate cos, you will get, so the differentiation will be over x. So cos will be sine omega t minus kx. So this is your del phi over del x. Now next you find out uz. So this is del phi over del z. So you tell me this expression. So this will be omega a sine hyperbolic of k multiplied by d plus z, and denominator will be sine hyperbolic of k d, and the other term will be, you differentiate how much, del phi over del z. So phi is this, differentiate with this with a cos, this will be uz. This term will be cosine of omega t minus kx. So this is your expression. Now you find in deep water, deep water, what happens? That is when Kd is infinity. Now, this omega A cos hyperbolic, this term, that is k d plus z over sine hyperbolic k d will approach a certain value. So, this is omega A e raised to the power k z. Now, the other term also will approach the same value. So, this you find out from hyperbolic expressions. So, omega A sine hyperbolic k d plus z over sine hyperbolic k d. So, this will also approach the same value. So, omega A e raised to the power k z. So, now you find out the resultant velocity u. U is root over of u square x plus u square z. So, this is omega A e raised to the power k z. So, at surface you put z equal to 0, velocity of water is u equals to simply omega A. Now, this is your velocity equations. You find out water particle path. Now, once you get this path, you will find the shape of the or the trajectory of the water particles. Now, how to find this? You obtain path by integrating velocity. By integrating velocity equations. So, what is actually your velocity ux? Ux is dx over dt. So, you get x if you integrate dx by dt. So, ux we have got as omega A cos hyperbolic k d plus z divided by sine hyperbolic, which is k d, and the other term is the sine expression omega t minus k x. Now, you try to integrate this. So, this is one equation. So, equation number 1, and the other u z is velocity is how much? dz over dt. So, u z we have got the expression as omega A sine hyperbolic k d plus z over sine hyperbolic k d, and sine, the other term you have got is cosine, cos omega t minus k x. So, this is equation number 2. Now, integrate these two. You integrate these two, you will get x and z. Now, if you integrate, you will come across a interesting conclusion. So, next class we will do this, and you will find that the water particle path is elliptic. You will get an ellipse. You try to do this, and this is your wave profile, and you will find ellipse coming. So, this is our z and this is our x. Sorry. So, water particle path is elliptic. So, we will explore this. We will try to find the equation of the ellipse. So, this is very easy. From this expression you can find out the equation for ellipse. Now, if you find out the equation of ellipse, you have to find major and minor axis. Find major and minor axis of ellipse. Now, in shallow waters you will find shallow water. Now, there will be two distinct cases, or rather 3 distinct cases. Number 1 is you find for deep water. Next, you find intermediate waters. The last category will be shallow water. Now, these are 3 cases we will come across. For all these cases, you find path of particles. So, next class we will do this, but before this we find out the equation of the ellipse. So, this is a discussion on the linear wave theory, and after this we will go to the nonlinear waves. Attendance you can give.